Look at this expanding constellation of data nodes. This visual captures the reality of the modern enterprise. We no longer secure rigid, metallic server grids or physical hardware perimeters. The definition of an asset has shifted to a logical, highly fluid ecosystem of data, metadata, and intellectual property. The core operational problem in this environment is that data is never static. It continuously changes physical states, moves across network boundaries, and alters its operational utility minute by minute. A traditional static perimeter defense cannot protect an asset that is constantly in motion. To solve this continuous state change problem, security architecture relies on the CISSP lifecycle. As mapped in this flowchart, the framework divides the existence of an asset into 6 distinct operational phases: create, store, use, share, archive, and destroy. True enterprise resilience requires an adaptive security model. By treating data protection as a continuous, state-aware lifecycle, an organization can map specific governance roles and precise cryptographic controls directly to these 6 distinct phases of existence. The lifecycle initiates here, at the create node, marking the exact point where new information is generated or existing data is significantly modified. Security engineering does not begin with the deployment of firewalls or encryption keys. It starts with objective valuation. This risk model calculates single loss expectancy, SLE, derived by multiplying asset value by the exposure factor, the exact percentage lost in a breach. We then multiply that SLE by the annualized rate of occurrence, how often we expect that threat to materialize in a given year. The resulting figure is the annualized loss expectancy, or ALE. Deriving the ALE provides the rigorous dollar value financial justification required before management approves any specific security investment. Executing this valuation introduces the concept of segregation of duties within data governance. The first critical role is the data owner. This is always a member of senior business leadership, such as a department head, who holds ultimate, non-transferable accountability for the dataset. They alone have the authority to accept risk, determine business value, and assign the classification level. Contrast this with the data custodian. Custodians are strictly IT architecture and administrative personnel. Their responsibility is limited to executing and maintaining the technical environment controls exactly as dictated by the data owner. Overlapping these roles inevitably causes systemic governance failure. Absolute accountability must remain with the business unit that understands the data's value, while the technical execution must stay firmly isolated within IT operations. Following creation, the data asset progresses into the store phase, where it is committed to a physical or cloud-based repository. This state is defined as data at rest. Because the information is inactive, its primary vulnerability vectors are the physical theft of the storage media itself or an unauthorized breach of the underlying storage infrastructure. To mitigate these specific risks, the global baseline control for resting data is the Advanced Encryption Standard, or AES. Specifically, organizations deploy AES utilizing 256-bit symmetric block ciphers, providing an exceptionally high degree of computational security. Technical custodians deploy AES 256 through mechanisms like full disk encryption, which protects entire volumes at the OS level, and integrate hardware security modules, dedicated physical devices that securely manage and isolate the cryptographic keys. Securing data at rest forms a mandatory static baseline of protection. However, that static encryption immediately becomes a processing bottleneck the moment the enterprise needs to actively use the asset. When data needs to move between systems or endpoints, it enters the share phase. Now classified as data in transit, it traverses active network pathways, exposing it directly to interception and man-in-the-middle attacks. Custodians secure this transit state by enforcing transport layer security, specifically TLS 1.3. By configuring TLS to mandate perfect forward secrecy, organizations ensure that even if a long-term session key is compromised in the future, previously recorded communication traffic cannot be decrypted. But the most critical vulnerability point occurs in the use state. As shown in this CPU schematic, the protective AES encryption layer dissolves, exposing the raw, plain text data directly within the processor. This is a computing limitation. To perform active computations, processors require data decrypted into plain text inside RAM. To mitigate memory scraping risks during this window, we use process isolation. Notice how this protective enclave barrier forms directly within the hardware. Technologies like Intel SGX create these secure, hardware-protected enclaves. They isolate specific execution threads, strictly cordoning off the memory space from any other running process. Architecting memory-level process isolation closes the final gap in operational cryptography. It ensures that the plain text data remains secure and unreadable to an attacker, even if the host's operating system or hypervisor is entirely compromised. When the asset in question contains personally identifiable information, or PII, cryptographic controls like AES and TLS are legally insufficient. Fulfilling strict regulatory mandates, such as the GDPR, requires applied privacy engineering. This data table demonstrates anonymization. By replacing identifiers with mathematical noise, we execute an irreversible transformation. Legally, the individual can no longer be identified. This completely removes the dataset from GDPR compliance scope. To maintain utility, organizations utilize pseudonymization and tokenization. Fields become generated tokens linked to an isolated key vault. Because tokenization relies on that separate, reversible key, the dataset can theoretically be re-identified. Under Article 4 of the GDPR, this means the information remains legally classified as regulated personal data, and the strict handling mandates still apply in full. Deploying the correct privacy engineering technique is a calculated business decision. It allows an enterprise to safely extract analytical value from highly sensitive data without inadvertently expanding their regulatory liability footprint. The lifecycle concludes in the final operational phases: long-term archive, which is strictly governed by legal retention mandates, and ultimately the destroy phase. The severe threat at this stage is data remanence. When physical storage media reaches its end of life, standard deletion commands leave residual traces of the asset fully recoverable by forensic tools. This infographic details the definitive framework for physical media sanitization, NIST Special Publication 800-88. It mandates 3 hierarchical tiers of destruction based on data sensitivity: clearing through systematic overwriting, purging via magnetic degaussing, and destroying through physical pulverization. But physical destruction presents an immediate complication for organizations utilizing multi-tenant cloud architectures. The enterprise client does not own the physical drives, making hardware pulverization impossible. The solution is crypto-shredding. Instead of targeting the physical disk, the enterprise executes the deliberate and verifiable destruction of the cryptographic keys used to secure the data. By destroying the keys, crypto-shredding instantly renders the logical asset permanently unrecoverable, fulfilling strict disposal requirements even within distributed hybrid environments. Modern asset security relies on this continuous architecture. It operates as an intelligent, moving wrapper around the data, enforcing the business accountability of the owner and the technical controls of the custodian from the exact moment of creation.
Welcome to This Explainer. Today, we are unpacking the rather terrifying rise of shadow infrastructure and exactly how you can securely govern your migration to the cloud. We're dealing with a monumental shift right now, moving away from those rigid, old-school physical perimeters and into dynamic, asset-centric governance. And as we're going to see, the stakes for getting this wrong have literally never been higher. So let's kick things off with a number that should make any IT leader sweat a little bit: $4.88 million. That was the global average cost of a data breach in 2024. That is a massive 10% jump year over year. But you might be wondering, what's actually driving this expensive surge? Well, it's not just super sophisticated hackers in hoodies. It is heavily driven by what we call unmonitored risk surfaces. Specifically, we're talking about exposures hidden in shadow data and completely unauthorized AI integrations. It's new tech being implemented right under the noses of central IT. And this data brilliantly illustrates exactly where those costs are coming from. Look at this. 69% of cybersecurity leaders either know for a fact or highly suspect that their employees are using prohibited AI tools. In the EMEA region alone, 39% of employees just openly admit to using free, completely unvetted AI tools for their work. They're bypassing security and pasting highly sensitive corporate IP and regulated customer data straight into these massive blind spots. And if we don't fix it, projections show that by 2030, over 40% of all global breaches will be directly caused by this unmonitored shadow AI.
To solve this huge governance gap, we're going to navigate 4 crucial concepts today. Number 1, the shared responsibility model. Number 2, securing multi-tenant environments. Number 3, zero trust and frameworks. And number 4, real-time AI governance.
All right, let's jump straight into part 1, the shared responsibility model, and really the myth of provider-only security.
Think of this foundational rule of cloud computing a lot like renting an apartment in a giant high-tech building. Your cloud provider, whether it's AWS, Azure, Google Cloud, whoever, they act as the landlord. They handle the security of the cloud. That means the physical building, the servers, the hypervisors, the data centers. But you, the customer, you manage security in the cloud. You are entirely responsible for locking your own apartment doors, managing your data, writing secure application code, and thoroughly vetting your guests. And that division builds out across different service models. Whether you're spinning up bare metal infrastructure as a service or just buying software as a service, there's one constant here. Data and identity are always unequivocally your problem. The complexity of what you manage might shift around, but your ultimate responsibility to protect your own data, that never, ever disappears. And guys, misunderstanding these boundaries is absolutely fatal. Industry analyst predicts that through 2025, 99% of cloud security failures will be the customer's fault. That is a truly staggering statistic. Almost every single breach won't be because your cloud provider failed, but because someone on the customer side misconfigured the services they were supposed to be protecting. Moving right along to concept number 2, securing multi-tenant environments. We've got to talk about shared storage and noisy neighbors. Because when you move your data out of your own basement and into the public cloud, you are stepping into a massive shared environment. You could literally be sharing physical hardware with dozens of other companies. And that introduces some very real architectural hazards, like the noisy neighbor effect. Imagine another company on your exact shared server suddenly running a massive resource-heavy data analytics job. If the environment isn't properly isolated, their workload monopolizes the entire system, and your app's performance suddenly just grinds to a halt. So how do we defend against this and prevent your data from accidentally crossing wires with someone else's? You have to be incredibly proactive. You must enforce aggressive logical isolation using sandboxing and namespaces. You need strict quality of service resource quotas to throttle those noisy neighbors. And most importantly for your data, you absolutely must use end-to-end TLS encryption while it's moving and transition over to customer managed keys or CMK when it's at rest. CMK is a total game changer because it means even the cloud provider themselves cannot access your data without your explicit authorization. You hold the keys. And honestly, this level of isolation isn't just a technical best practice. It's a strict legal necessity. Let's look at highly regulated spaces like healthcare, for example. Shared load balancers or storage arrays could accidentally bleed protected health information right across organizational boundaries. Weak tenant isolation here doesn't just mean you have a slow app for an hour. It means catastrophic exposure of patient data and massive HIPAA regulatory violations. Which brings us perfectly to our third concept, zero trust and frameworks, or how we establish the completely new identity perimeter. Because let's face it, the old physical perimeter, the actual walls of your corporate office, is totally gone. So how do you actually build a fence in a shared cloud environment? You shift your perimeter entirely to identity, and you ground it in the core zero trust mantra. Never trust, always verify. You could no longer trust a user or a laptop simply because they happen to be plugged into the office network. You can't just trust someone because they logged in successfully at 9 a.m. No way. Every single system request needs continuous authentication. We enforce the principle of least privilege, meaning users only get access to the exact resources they need for their specific job and nothing more. This is absolutely crucial for limiting the blast radius if their account ever does get compromised. You add in mandatory multi-factor authentication and conditional access policies, like, say, demanding a fully encrypted device before granting access, and suddenly you've built a modern, highly resilient defense. Now, you don't need to reinvent the wheel to settle these complex locks up properly. Smart teams rely on standardized roadmaps. Things like the Cloud Security Alliance's Cloud Controls Matrix, which gives you 207 specific controls mapped to international standards. Or the CIS controls. Take a look at that key detail there. The latest version of CIS directly targets these modern hybrid setups with a brand new service provider management control. It literally gives you an exact roadmap for securely governing your vendor relationships. And finally, let's look at part 4, real-time AI governance. We have to secure the future of artificial intelligence workflows. Let's circle all the way back to that terrifying shadow AI problem we started with. Traditional security tools are great at reviewing logs and telling you exactly how you got hacked 3 weeks ago, right? But that is totally useless today. With massive incoming regulations like the EU AI Act applying in August 2026, relying on slow, manual log reviews for instant AI generation is completely unacceptable. The sheer speed of AI data generation requires an immediate, automated response.
So to fix this, modern organizations are deploying active AI compliance copilots. You're building a real-time chain of custody. You capture the original input prompt, you log the exact model version, and you record the generated response. And the craziest part? This entire valuation, checking for sensitive IP, enforcing reductions, it all has to happen in under 20 milliseconds. It literally turns audit preparation from a manual nightmare into just a continuous, real-time operational byproduct.
So when we combine those established frameworks with layered security, continuous zero-trust verification, and lightning-fast runtime AI governance, we can confidently secure the modern cloud estate. It takes moving way beyond simple checkbox compliance. And that leaves us with one incredibly crucial, provocative question for you to ponder about your own infrastructure today. Is your organization managing its AI, or is your unmonitored shadow AI managing you? Take a hard look at your asset inventory and ask yourself what might be lurking in the blind spots. Thanks for hanging out with me for this explainer, and I will catch you next time as we continue to decode the technologies shaping our world.
As organizational infrastructure transitions towards distributed and cloud-centric models, the traditional perimeter-based security model is replaced by a decentralized architecture of individual nodes. This shift changes the landscape for sensitive assets, such as a 16-digit credit card number, which now frequently exist outside the protection of a localized internal network. The core challenge is maintaining high data accessibility for business operations, while ensuring strict confidentiality against interception by unauthorized entities. Implementing mathematical cryptography provides a necessary logical defense, but it represents an incomplete security posture if the physical media hosting that data is not equally governed. A high-assurance security model requires a continuous link between technical software controls and the administrative protocols that manage physical hardware. We will analyze this integration by tracking a single data element from the moment of ingestion through its entire digital and physical lifecycle. Effective security is the result of engineering a rigorous lifecycle that accounts for the state of the data at every stage of its existence. The lifecycle begins at the point of ingestion, where raw data is introduced into the organization's digital environment. Standard symmetric encryption transforms plain text into ciphertext, often creating structural mismatches that break database schemas. While format-preserving encryption fixes this, it adds latency. Alternatively, tokenization replaces the sensitive data with a non-sensitive placeholder, storing the original in a secure vault. This token is designed to mirror the structure of the original data, allowing it to validate against algorithms like the Loon check without exposing the actual sensitive information. The use of tokenization is a strategic choice for organizations subject to the Payment Card Industry Data Security Standard, or PCI-DSS. Because a token has no mathematical relationship to the sensitive data it represents, the systems that store only tokens are typically removed from the costly and complex PCI audit scope. However, vaulted tokenization introduces a dependency on a central repository, which can create a single point of failure and introduce network latency during high-frequency lookups. Vaultless tokenization mitigates this by using hardware security modules to resolve tokens mathematically, providing improved scalability and reducing infrastructure overhead. By substituting representation for mathematics at the point of ingestion, organizations can protect legacy infrastructure and reduce their overall regulatory burden. As the token travels from the internal network to an external payment gateway, it enters a transition phase where it must be protected in transit. Transport Layer Security, or TLS, creates a secure communication channel. This ensures that even though the payload is a non-sensitive token, the session itself remains confidential. TLS uses asymmetric encryption to solve key distribution. The sender uses the recipient's public key for encryption, reversed only by the corresponding private key. Because this is computationally intensive, the system switches to symmetric encryption to handle bulk data efficiently. While these methods protect confidentiality, the system must also verify integrity, ensuring the data has not been altered during transport. This is achieved through cryptographic hashing, such as SHA-256. A hash function transforms the data into a fixed-size character string, or digest, which acts as a unique digital fingerprint. High collision resistance ensures that even a single bit of change in the input data results in a completely different hash, a phenomenon known as the avalanche effect. This allows the recipient to instantly identify any data corruption or tampering. This layered defense ensures that value is removed by tokenization, the channel is secured by AES, the handshake is protected by asymmetric keys, and integrity is guaranteed by hashing.
While logical controls protect the data during processing and transmission, the hardware where that data eventually resides requires its own set of physical protocols. Physical media handling has been a core security component since early computer rooms of the mid-20th century, where tape drives required strict access controls. Today, these requirements are codified by the National Institute of Standards and Technology, or NIST, through frameworks like Special Publication 853. The Media Protection Control family provides an additional layer of defense. It ensures that while encryption at rest secures the data mathematically, the physical media is also protected from unauthorized handling or removal. Control MP3 focuses on media marking, requiring physical labels that indicate the sensitivity of the data. This provides clear handling instructions for personnel who interact with the hardware. These markings dictate the storage and handling protocols required by the organization, scaled to the security categorization of the system. Control MP5 addresses the high-risk activity of transporting media outside of controlled areas, mandating the use of secure containers and specialized couriers. Accountability is maintained through a rigorous chain of custody log, documenting every person responsible for the media until it reaches its final destination. Integrating media protection frameworks ensures that a security posture is not reliant on a single layer of mathematical defense, but is reinforced by strict physical governance. The final phase of the data lifecycle occurs when the storage hardware is decommissioned or repurposed. NIST Special Publication 800-88 provides a risk-based hierarchy for sanitization, detailing the actions of clear, purge, destroy, and cryptographic erase. The clear method uses software-level overwriting to protect against non-invasive data recovery, making it suitable for media being reused within the same organizational context. For magnetic hard drives, the purge method often utilizes degaussing, using a strong magnetic field to disrupt the stored data bits on the physical platters. This process is ineffective for modern solid-state drives and flash memory, which store data through electrical charges rather than magnetic domains. Furthermore, SSD wear leveling algorithms can prevent traditional overwriting from reaching all data locations, leaving potential remnants on the drive. Consequently, SSDs containing high-sensitivity data may require firmware-level purges or physical destruction, such as shredding or pulverization, to ensure the data is unrecoverable. Cryptographic erase provides a highly efficient alternative for self-encrypting drives. By securely erasing the media encryption key, the system renders the encrypted ciphertext on the drive permanently unreadable without the need for physical destruction. Ultimately, the method of sanitization is determined by the specific hardware architecture of the storage medium and the sensitivity of the data it holds. This comprehensive journey demonstrates that data protection is not an isolated event, but a continuous series of integrated controls. Organizations utilize tokenization to reduce compliance exposure, encryption to maintain confidentiality in transit, and hashing to verify data integrity. These logical safeguards are supported by physical media protection protocols and rigorous sanitization standards that ensure data remains secure at rest and at the end of its life. Advanced security architecture treats mathematical algorithms and physical governance as two interdependent halves of a single unified posture. True high-assurance security is achieved when an organization meticulously governs every state of data, from its mathematical creation. Hey everyone, welcome back to The Explainer. Today, we're taking a really fascinating look at the absolute backbone of modern information security. Now, I want you to meet our protagonist for today's journey, your organization's most sensitive data. We're going to map out its entire life cycle, literally tracking it from the exact second it's born all the way to its absolute permanent destruction. So here's how we're going to break this all down. First up, identifying the crown jewels. Then, roles and accountability. The 3 data states, privacy and retention, defensible destruction, and we'll wrap up with AI and emerging threats. Okay, let's just dive right into this chronological journey of asset security.
Section 1. Identifying the crown jewels, birth, and identity. Let's get into it.
To really understand the massive stakes involved in modern security architectures, we've got to define what we mean by crown jewels. And we aren't just talking about physical servers or networking hardware here. The real value for companies today lies in intangible assets. I'm talking about your intellectual property, those proprietary algorithms, and of course, highly sensitive customer data. Here's the thing though, you absolutely cannot protect an asset if you don't even know it exists. If you lack an automated inventory, you're basically either way overspending on unnecessary protections, or worse, you're leaving catastrophic gaps wide open. Imagine trying to guard a huge museum, but you have no idea which rare artifacts are actually inside the building. Right? It's an impossible task.
So, once we actually know the data exists, it has to be classified right at birth into standard commercial levels. Up at the top, we've got confidential. These are your trade secrets where any disclosure means exceptional damage. Then it steps down through private for things like employee PII, down to sensitive for internal policies, and finally all the way down to public, stuff like press releases. But hey, here is the absolute crucial takeaway. Classification isn't permanent. Think about it. A top-secret acquisition plan today is literally a public press release tomorrow. We have to constantly review and downgrade data as it ages. Why? Because it drastically reduces management costs and legal liabilities. Holding on to maximum security restrictions for data that just doesn't need it anymore, it's a massive drain on resources.
All right, moving on to Section 2, roles and accountability, guardianship. Now, what's really interesting about this slide is the sharp, undeniable line drawn between accountability and responsibility. It's a key distinction. On one side, we have the data owner. This is usually a senior business executive, like a CEO or a department head. They hold the ultimate accountability. They evaluate the business impact and basically dictate what should be protected. Now, on the flip side, we have the data custodian, who is typically sitting right there in the IT department. They handle the technical responsibility. They're the ones implementing the backups, the encryption, the access controls. So the custodian is essentially answering the question, how do we technically protect it? To put it simply, the business leader decides the what and the IT admin executes the how.
That brings us to Section 3, the 3 data states, the active life.
As our data goes to work, it basically exists in 3 distinct states. First, there's data at rest. It's just sitting there on hard drives, relying on full disk encryption. Then we have data in transit, which is moving across networks and is protected by secure protocols like TLS. But data in use, well, that has historically been our massive vulnerability. Why? Because data always had to be decrypted in the system's RAM just to be processed. But today, thanks to some truly incredible emerging tech like trusted execution environments, which hardware isolate data, and homomorphic encryption, we can actually perform complex mathematical computations on data while it remains fully encrypted. Guys, it is a total game changer. It literally means a cloud provider can process your data without ever actually being able to read it. How cool is that?
But beyond just encryption, we also deploy these specialized technical enforcers. Think of them as bodyguards. First, there's digital rights management, or DRM, which is incredible because it actually travels with the data. It prevents a user from, say, copy-pasting a document even after they've gotten legitimate access to it. Then there's data loss prevention, or DLP. This acts like a strict border guard, blocking unauthorized movement, like trying to copy sensitive files over to a USB drive. And lastly, as employees increasingly bypass IT to use unsanctioned tools, like firing up an unapproved personal Dropbox just to share some files, Cloud Access Security Brokers, or CASBs, step right in. They secure these SaaS environments and hunt down all that risky shadow IT. All right, moving into the later stages of life. Section 4, privacy and retention, the aging process. Now pay attention to this one because this distinction is a massive compliance pitfall for modern organizations doing data analytics. It comes down to anonymization versus pseudonymization. Anonymization is completely irreversible. The data can literally never be traced back to a specific person, meaning it is entirely exempt from strict laws like the GDPR. Pseudonymization, on the other hand, well, that merely replaces identifiers with reversible artificial codes. And because that key to reverse it still exists somewhere out there, pseudonymized data leaves your organization fully subject to privacy laws and legally exposed. Let me be clear. Treating pseudonymized data as if it's completely anonymous is a fast track to some massive regulatory fines. Don't do it. Part of this whole aging process is dictating exactly how long we legally have to keep data alive. For example, the IRS requires tax documents to be kept for 3 to 7 years. HIPAA requires healthcare policies for 6 years. SOX demands 7 years for financial records, and PCI-DSS requires audit logs to be held for 1 year. Now, storage is super cheap these days, right? So companies often just default to hoarding data. But here is the absolutely crucial security takeaway. Keeping data alive a single day longer than legally necessary just increases your attack surface, period. A breach of some decade-old database that should have been deleted years ago, that is an entirely preventable disaster. So when the clock runs out, the data needs to go.
Which brings us to the dramatic finale, Section 5. Defensible destruction, the end of the line. So to completely eliminate the risk of data remnants, which just means data being recovered later on, we rely on the NIST 880 framework. And this brilliantly illustrates how the method escalates in severity based on the data's classification. Step 1 is simple disposal. That's fine for harmless public data. Step 2 is clearing. This is a software overwrite, perfect if you're just handing a laptop over to another employee. Step 3 is purging. This involves using heavy magnets or cryptographic erasure for media that's leaving the building forever. And finally, step 4 is absolute physical destruction. The rule of thumb here is that you must systematically match your destruction method to the data's initial sensitivity. But here's where things get wild, because the actual physics of destruction have completely changed. If you have an old-school magnetic hard drive, sure, you can wipe it with a giant magnet called a degausser. But modern solid-state drives, they use electrical charges and flash memory chips. Magnets do absolutely nothing to them. Nothing. To truly destroy an SSD today, you have to physically shred the drive into pieces smaller than 2 millimeters. I'm serious. If a piece is even slightly larger than that, a single microscopic intact NAND chip could still allow an attacker to recover your crown jewels. The physical reality of modern memory literally requires absolute physical annihilation. Finally, let's look at the new frontier. Section 6. AI and emerging threats, the unknown future. It is honestly the most serious question in modern security right now. So how do you protect an AI's brain? We are now forced to classify entirely new types of assets. We're talking specifically about training data sets and the model weights themselves. And these are highly, highly vulnerable. There's data poisoning, where attackers subtly alter the training data so the AI actually learns to ignore specific malware or even leak sensitive information. And then there are adversarial attacks, where inputs are manipulated just to force the model to fail. The old principle of least privilege, it can no longer just apply to human employees. It has to actively apply to the autonomous AI agents that are out there processing your data. Which ultimately leaves us right here. The shift in modern security is completely undeniable. We are rapidly moving away from those outdated perimeter defenses, and we're focusing entirely on true data-centric asset security. You literally have to protect the data at birth, while it works, as it ages, and straight on through to its permanent defensible destruction. So I'll leave you with this to think about. Are you truly protecting your organization's data throughout its entire life cycle? Or are you just building a giant wall around an empty castle? Thanks so much for joining me on this explainer, and I'll catch you next time.